Okay.
Someone else waiting outside?
Anyone else?
Someone
Now's your chance to come in.
Going to be a nice talk. Next talk is by Hillebrand, or by Hill as well, on superdense coding.
Okay, well hello. I'll be talking about superdense coding and quantum key distribution today. And these two protocols, they're part of my MSc thesis that I wrote last year with Bob Cook in the Oxford Computing Laboratory. It's called Quantum Protocols Involving Multi-Particle Entanglement and Their Representations in ZX calculus. Very nice. So what did I do in my MSc thesis? I looked at lots of existing quantum protocols, about 25, and I represented them in the ZX calculus. And I tried to find an alternative way to prove that they work, so that they do what they're supposed to do. So, as you'll probably know, most quantum protocols are traditionally presented in Dirac notation. This is quite low level, can be quite tedious, regrouping terms, and I think most importantly, it's not always clear what's going on, because it does not capture entanglement in a very clear and intuitive way. So for example, if you have this state and this state, they look a lot like each other, but they're very different in terms of entanglement, because the first one is not entangled at all, and the second one is actually maximally entangled. So it's very different. So now let's take the ZX calculus, also called the red-green calculus, because it consists of red and green dots mostly. This is a more high-level language. It's graphical, so you can sort of see what's going on. The topology of the graphs that we'll be looking at is very important, and this sort of exemplifies the flow of information. So this is especially useful for protocols that involve an exchange of information, such as teleportation, quantum key distribution, that sort of things. And I think this is one of the most important things. Instead of regrouping terms, as you do in Dirac notation, you're rewriting diagrams. And this is done by a few quite simple rules, I believe. So, what are we going to do right now? First, I'm going to present some basic constructions and the way they look in ZX calculus. Then we'll talk about the basic rules or the basic actions that govern the ZX calculus. We'll look at some derivations of those. Then we'll talk about the algorithms, the sort of algorithms that I use the ZX calculus for, the sort of algorithms. And we'll look at two of those algorithms in particular, namely superdense coding with GHZ and pairwise key distribution with W. And then I'll tell you some of my conclusions. So first, the ZX calculus is based on these two circles basically. So x plus plus, x minus minus, and z plus and z minus. And this is what they look like. So we have, these are the x states. We have a 0 and a pi here. So we have dots with a phase. The phase goes from 0 to 2 pi. And then for the two z states, we have two red dots with phase 0 and phase pi. So the next important thing is the Pauli matrices, of which we have 4. The identity matrix is just a wire without any dots. This is not very clear. So the Z gate is a green dot with phase pi. The X gate is a red dot with phase pi, and YI is a combination of the two. So we'll be using those later on. So if two particles are maximally entangled, we of course get the 4 different Bell states. They're quite important. Note that they all have a green and a red dot, and it just exchanges phases basically. So we have 0, 0, pi 0, 0 pi, and pi pi. And you get.
So what's in the ones and zeros in these boxes, right?
They're the faces of the dot. Basically.
The ones and zeros and the boundary vertices.
Yeah. Oh, so they're not really that important. This is an input and this is an output, or the other way around. We don't really distinguish between those here. But it's basically to indicate that the wire ends here. So the gray boxes, they're just where you go in and where you go out. So this is to indicate that we have 2 qubits. And they're connected. Does anyone?
Just maybe the number of people.
Hmm?
Just maybe the number of people.
Yeah, I blame quantumatic.
For example.
We'll get to that later. Okay, so I'm not that interested in two particles that are entangled. I'm more interested in multi-particle entanglement because it's more complicated. So there's two inequivalent ways in which three particles can be entangled, and one of them is called the GHZ state. It has a very easy graphical representation, and this is what it looks like. So we have three qubits, and they're just connected, all three of them. And the other way would be the W state. This one's slightly more complicated, and we'll see also when we start reasoning with this one that it will be slightly more complicated than the other one, but we can still get some nice results about that. And then finally, the controlled NOT gate. As you all know, a controlled NOT gate that takes in two qubits, a control qubit and an input qubit. And this is a control qubit, and this will be the input qubit, and it will be flipped if this one is wrong. Okay, so now we have all our building stones, and we'll use those later to glue together the representations. But once we have those, we want to be able to rewrite them, and we're going to do that according to these rules. So let's shortly go over them. So the first rule, the T rule, only the topology matters. Informally, this means we can yank the wires. So I can take this dot and I can move it anywhere I want as long as I preserve the number of inputs and outputs. Note, however, this does not mean that all the other rules preserve the topology, because they don't. Not always, at least. But this one, it does. It just means yanking it. So the second two rules, S1 and S2, are also called the spider rules. So what we have there is that if we have a green dot and a green dot here, and they meet at some input and output, we can sort of morph them together and add their faces. And what we also have is if you have a dot with phase 0, so this one has phase 0, we can omit it. We can just leave it out. So that brings us to the B rules. We can sort of push the red dot through, and then we'll have two separate ones. And we can replace this little cross here by this, and then we switch to colors. In the K rules, we see that the pi, it will distribute among all those outputs. And we also see that if we push an arbitrary phase to a pi, that we put a minus sign in front of it. The C rule is, there's supposed to be an alpha here, but sometimes it just doesn't show in certain PDFs, so I'm sorry about that. So here's an alpha. Then we just plug Hadamard gates all around it, and then we can change the color. And these are some rules about scalars, but we will not be talking about those today. So let's skip that. So there's a rule that we can derive from this. It's called the Hopf law. Basically means if we have a construction like this, these two connections will disappear. It's not that hard to derive, but I don't think we'll have time for that here. And another rule that we can derive, I've called this the A rule. It doesn't really have a name. So if you have an alpha here and a pi here, the pi will disappear and we get a minus here. And you can also do this with the colors reversed, of course. So this one's green and this one's red. Okay, so now we have all our building stones. So what sort of algorithms can we look at? Well, I've looked at teleportation, and then two different kinds. I've looked at teleportation protocols that use multi-particle entanglement, so use the GHZ state or the W state to teleport things, but also teleportation of entangled states. So there are some protocols that teleport to entangled qubits. It's quite cool. You can do that as well. So superdense coding, that's what we'll be talking about today. Superdense coding with the GHZ state, which means that you will be transferring a number of qubits, and that way you'll be transferring more classical bits. That's what's called superdense coding. We'll be looking at that today. Quantum secret sharing. With quantum secret sharing, you share a classical bit string with a group of people in such a way that the other people have to work together in order to retrieve the state. And you can do something similar, but not just for a classical string. You can also do it for quantum state itself, that they have to work together in order to retrieve the state again. Furthermore, I've looked at leader election. in a leader election protocol, there's a number of participants. Every participant will have the same chance of becoming the leader, but only one of them will become the leader at the end of the protocol. And you can do that with the W state. And finally, I've looked at lots of different quantum direct communication protocols, which is a protocol which you can safely communicate with others without first sharing a key. So in that sense, it's different from cryptography. So right now, we're going to look at superdense coding with GHZ. So this is what we're going to do. We have two participants in this protocol, Alice and Bob. And Alice and Bob start by sharing a GHZ state. Bob has the first qubit and Alice has the other two qubits. Then Alice can apply a combination of the Pauli matrices on both her qubits. And then she will transfer her qubits to Bob, so then he has all three of them. Bob will measure all three of his qubits, and then he will retrieve 1 out of 8 states in a GHZ state. And with that, he has 3 classical bits. Are there any questions about that? Alright, let's keep going. So there's 8 different states in the GHZ class that we can distinguish by measurement. This is the first 4, and the other 4 will be very similar. There's actually 16 different ways you can apply Pauli matrices to the GHZ state, but there's only 8 you can distinguish. So if you would apply, for example, this one would be equivalent to applying a Z gate here and here, because they will morph together and will form a 1. So we cannot distinguish between that, even though it would technically be a separate state. So we have 4 different ones. This is just the plain GHZ state as we saw before. And we can retrieve all the others by applying Pauli matrices to this qubit or both of them. So this one you get by applying an X gate to the second one, next gate to the first one, and next gate to both of them. And then we move on. Oh, that doesn't help. And then we move on, and you see that it's the same as we had before, only instead there is a Z gate here everywhere as well. Okay, so we have 8 different ones, and then we want to measure them. And this is what measurement into the GHZ basis looks like. This comes from a quantum circuit and then translated into the ZX calculus. So here will be our GHZ state, and then what comes out here will be 3 qubits in the Z basis. So we'll get some form of zeros and ones. And then if we translate them just to zeros and ones, we'll get a binary number, and that will be the number of the state. There's a very nice way of encoding this, but we don't have time to go into the details. Okay, so this is what the first one will look like. So this is just a normal GHZ state. Then we have our measurement right here. And then we can start applying the rules that we discussed before, and we'll see what comes out. So to go from here to here, you apply a spider rule. So you just morph all these green dots together, and it will look like this. Then to go from here to here, you can apply the Hopf law. So you'll see we have 2 of these nice things. So those will disappear, and this is what we'll end up with. And then over here we can apply the C rule, and we can change the color of this one. And we end up with 0, 0, 0, which is the first state in our GHZ class. And we'll go through the other ones a little more quickly because they're all quite similar. So this is the second GHZ state. And we'll just apply the same rules. So the spider rule right here, the Hopf law, and the C rule right here. And we'll end up with 0, 0, 1 in the second state in our GHZ class. And we can keep going. This is all quite similar, but you see that the numbers change. We essentially keep applying the same rules. So, we've seen, we arrived at the last one, we apply the same rules again, and then we get the last one. So, we have now shown, by the means of ZX calculus, that we can indeed distinguish between the 8 different states in GHZ class by means of measurement, and by that we have transferred 3 classical bits by only transferring 2 qubits. So this protocol works. Okay. So let's move on to the next one. This one is a little more complicated. It's called pairwise key distribution with W. So this time we have 3 participants. They're called Alice, Bob, and Charlie. So Alice, Bob, and Charlie share a W state. Each of them has 1 qubit. And what they're trying to achieve is that they will be sharing a key with pairs of them. But they can't decide in advance which 2 people will be sharing the key. So they all measure their qubit at random in either the X or the Z basis. And then they announce their measurement direction, not their outcome. And then in the 3rd step, they can choose to randomly announce their measurement outcomes as well. And this is to check for eavesdropping. So if you get illegal measurement outcomes, then someone's been messing with your channel and someone is doing something to it. But let's assume they don't, and they keep going. Then, if the overall measurement basis is 2 X's and 1 Z, they'll have a valid measurement basis, and they'll keep going. So let's assume they do that. And then the one who measured along the Z-axis, she or he will be the decider of the protocol, and the protocol can only continue when Z plus is obtained. And when this is the case, then the 2 people that measured in the X basis will now know that they have the same measurement outcome in the X basis. So they now share a bit. And they just keep repeating this protocol until they have enough bits to have their key. And if they find out that someone's eavesdropping along the way, then they'll start over again. Okay, so what does this look like in a ZX calculus? Well, this yellow thing over here, that's our W state that we saw before. And there's 3 outputs. One of them is measuring in the Z basis, and one of them is measuring in the X basis. And what we want to show now is that if this outcome is 0, so the decider has outcome Z plus, then this person will also get the outcome alpha. And alpha is either 0 or pi. So it's either plus or minus. Okay, so this is very easy to show. So this is what it looks like. This person, the decider, will have a 0 outcome, and this one has alpha either 0 or pi. And then we're applying a few rules at once, so this is a complicated step. So we apply S, so we morph this one to there, we get pi. And what we also do at the same time, we apply the K rule. So we push this one through, it will become a minus pi over 3. And then these 2 obviously cancel and we leave them out. So this is what we end up with. Then we can apply the S rule again. We morph all 3 of these together. And since we set the faces are modulo 2 pi, we'll end up with a pi here. And we have pi over 3 right here. Then we can apply the Hopf law again. We'll end up with this. And then we can apply the A rule, and we'll end up with an alpha as we required. So you can also show that if there's an outcome of pi over here, that the entanglement will actually break, and the protocol doesn't work anymore. Yes?
What does this remaining dot in the end?
Okay, so this is a scalar. If there's no inputs and outputs, there's a scalar, but we've decided to leave scalars out, so you can ignore that. Okay, so we now have shown that also pairwise key distribution works. So, what's the hard part about this? The hard part is finding the diagrammatic representation. Because before you can do it, you need, well, all those basic instructions I showed you before. You sort of need all the different little parts. You need to know what a W state looks like. You need to know what a measurement looks like. All those different parts. And then you kind of glue them together. So that's the hard part. Like, what does it look like when I've done all the steps in the protocol? What do I have? And after that, it actually gets really easy. Because then you just have to rewrite the diagrams. And as we just saw, that's not very hard. And it gets even better. There's a program who can do it for you. It's called Quantumatic. I've used Quantumatic to make all the pictures. And it's getting better and better. You can also put other theorems in now, like not just the ZX calculus, but the red, green, blue calculus. calculus that we'll talk about later, and the GHZW calculus, and all sorts of other stuff. And quantumatic, well, we're trying to make it do arithmetic rewriting. That doesn't work that well yet, but if you stir it a little bit, then it will usually get you to the state where you want to go. So the rewriting part is not the hard part, it's finding the diagrammatic representation. We're almost done. So something that we didn't really discuss, that I kind of skipped over quite quickly, is the security of the protocol, and this is where those scalars come in again. Because in order to check the security of a protocol, you're sort of calculating the probability of getting illegal measurement outcomes. So measurement outcomes that you can only get when someone tampered with your quantum channel. And so far, this is not exactly possible in the ZX calculus. And this is mainly because we left out the scalars all the time. So we can calculate if we plug something, we can calculate what we get. We cannot calculate what the probability is of that. So I think for that, we will still need the augmentation. So what I propose is a joint approach, and that's to represent protocols in both ZX calculus and Dirac notation. So I think reasoning in ZX calculus is actually a lot easier, more intuitive, better than regrouping terms in the augmentation. So that's what I believe for. So to close this off, if you're at all interested in this, I encourage you to have a look at my master thesis, and this is where it can be found. And this was it for today. Any questions?
Right at the start of the talk, you mentioned that in the Dirac notation it's hard to distinguish this is a pure state, this is an entangled state. So does your notation improve this? If you look at the picture, can you see this is an entangled state or is this a pure state?
Yes, you can. Let's go back to, for example, the okay, so these are the Bell states, and the reason they are entangled is because they're connected. If this would be 0, 0, you would have two dots separately, and we won't be connected. And that's how you can easily see that.
So if you go to the dense coding slides, where you have a big mass of connected dots, so from the end it's a pure state.
Yeah, that's true. We start out with an entangled state, that's the important bit. Okay, so yes, we started out with this, which is obviously entangled, and then we rewrite it, and then it's not entangled anymore. That's true.
So this looks entangled, there's all sorts of wires.
Okay, so I think it's important that when you look at a state, you don't just look at this, but that you look at what it actually entails. And what you're trying to do is you're measuring it. This is a measurement circuit. So of course you're breaking the entanglement, because that's what happens when you measure things.
So you're saying if you like simplify it in some way, then it becomes clear.
Yeah. So when you do the rewrites, you obviously see that it's not entangled anymore. But the reason it's not anymore is because you're measuring it. You're making it not entangled.
So in your conclusion, you say that the Dirac computation may account for probability.
Yes, I think so.
Okay, but if you do it carefully with this, you can compute also the probability.
I think it should in theory be possible, but at the moment we don't really know what scalars mean, like what their worth is. We know what they look like, but we don't really know what they are. And I think also before you want to do that, like for example, quantumatic, these are all scalars. There's a lot of rules, as we saw before. You see those little triangles that I just kind of ignored? These, well, they're all left out in quantumatic. So if you want to calculate with scalars again, they will all have to be included again.
But for the security effect, I think it's the point is how you model the attack. If there is a need to occur, what is the action of the user, and how you model this
Well, so it depends on the text. I did look into this in my master thesis. We studied all the quantum direct communication protocols, and some of them you can do quite easily. For example, when Eve entangles a qubit with the quantum channel and stuff, and you can see what happens. What is really important is not that she does that and what that looks like. It's important that what kind of illegal state she creates with it, because that's the only way for you to detect that she's actually there. So you can model it, but it won't help you as long as you don't know what scalars are.
Question? Sure.
As I understand, so you now in your formalization, the classical reasoning, the classical communication and classical reasoning is on the metadata, right? So it's rather simple, and you basically do all the case distinctions.
Well, yeah, you could the quantum direction of the superdense coding. You can do that a little more general than I've done now. Because what I did later on is so one of those GHZ states, you can model that as having a red dot here, a red and a green dot here, and a red dot here, and just give them a variable that is either 0 or pi. And it turns out that you can still apply most of the rules with that. Like if you think it through, because all the rules either apply to 0 or pi. So you can do this a lot quicker than I've done it now.
And that's like, can you like, if you want to incorporate, like deal with some more complicated classical reasoning, like do you think it's possible to like actually include such classical communication in your diagrammatic targets?
It's sort of included, like for example the teleportation protocol, where you need classical communication to correct for your measurement outcome basically. It is included in the sense that you get a variable appearing twice. So if you would do the teleportation protocol, you would have a measurement here, and it would have, like for example, outcome alpha, and then that alpha would appear again on the other side. And that would be the encoding of the classical communication. Because they need to be the same in order to cancel each other out.
I mean, like, can you do it modularly? Like as I understand, like, your quantum part of the diagrammatic calculus is quite modular. So you have this entangled state, and you have measurement, and you just like put these two graphs together. Right? Then on classical reasoning, do you think you can do that?
What do you mean by classical?
So if the measurement happens, then you put this, and then like if you case this, like if you distinguish cases.
Yes. Yes. This is what I tried to explain to you. So let's, for example, do teleportation. So that's a really easy protocol. So we have alpha and beta here, and they're either 0 or pi. So in a teleportation protocol, we start out with an entangled state, and then Alice will be here, and Bob will be here. So we have our unknown state here, and we will call it phi. And then what Alice does is she makes a measurement into the basis, into the bell basis. So this is what that looks like if you get that. And that will be gamma and delta, for example. And then Bob will need to apply the same ones on this side in order to correct for those. And that would be the classical communication that we talked about. So in the protocol it will say, Alice calls Bob and tells Bob, I've got this measurement outcome. So in our representation here, this will be the same, because this one corresponds to this one, and this one corresponds to this one, and this is the reason why they cancel out. So you can do it more general, yes.
I think there were 3 more questions. We have for one. You were the first, and then I think we can have coffee and
Almost everything in mind.
Just very quickly, so what are the limitations of this calculus? I mean, I presume you cannot represent every state with it. I think you can only represent a finite set of states. Is this correct? Or can you represent
so
every quantum state?
It's easier to present states like this. For example, the GHZ state and the Bell states and stuff. They're quite easy because they have...
I thought you are confined to the stabilizer formulas, but that cannot be true.
Yeah. So no, that's not true. You can make more general states, but they won't be as nicely.
Okay, thanks.
The problem though is you can make them, but they won't be as nicely behaved. You can calculate what average state looks like, but this state behaves so nicely because it only has faces 0 and pi, and we have all kinds of really nice rules for them, so we can reason with them. But you can make any state, which is like anything between 0 and 2 pi.
Okay, let's leave the other questions for coffee.